So welcome everyone to our seminar on probability stochastic process from USP. And today we have Bernardo, Nunes, Borges de Lima from Federal University of Minas Gerais. So welcome Bernardo for accepting the invitation, and welcome, thank you, and welcome to our seminar.
Okay, can I start?
Yeah, sure.
Thank you very much, Aline, for the invitation. For me, it's a pleasure to speak in your seminar. One of the reasons that the first talk that I gave, just I finished my PhD, was in the probability seminar of USP when Fabio invited me several years ago, something like 18 years ago. And I think that it was my third time in the USP probability seminar, and it's ever a pleasure to speak again here. Then, for some of you, certainly for Eulalia, perhaps from Renato, the first part of my talk is in some sense not new, because this problem certainly is the probability question that I use more time in my life to thinking about, the truncation question. This question was, I will explain later what is this question, but this question was told me by Vladas and Eulalia when I was a PhD student. I think that originally this question was proposed by Professor Henrique Angel a long time ago. And okay, let's start. Here we will consider a long-range bond percolation model. Oops. Okay, a long-range bond percolation model. Suppose that our graph is the hypercubic lattice, ZD. In principle, D can be at least 1. And we have the set of oriented bonds. That is, we have bonds starting from any vertex, and the other endpoint of the bond is along some coordinate axis, that is, from this vertex x, from this vertex x, start long-range bonds parallel to the coordinate axis with all lengths. Okay? We have only bonds parallel to the coordinate axis, no diagonal bonds. And we also have a sequence of numbers, pi, a sequence pi of numbers on the interval 0, 1. And we can think that pi is the probability of each bond with length I is open. And all bonds are open or closed independently of each other. That is the probability space that describes this model is the 0, 1 to the power e, that is 0 is denoted that some bond is closed, 1 some bond is open. The sigma algebra is the canonic product sigma algebra, because we are supposing that all bonds are open independently. And the probability measure, P, is the product of Bernoulli measures with parameter P, pk, where k is the length of the bond. And as usual, I will use this notation, 0 connect to the infinite, to denote the set of configurations where the origin is connected to infinitely many vertices. And what's the truncation question? The truncation question, it's very easy to state. fix some positive integer number, k, and we will define and given also the sequence pi, we define the truncated sequence pik, defined like this. The chi-if term of the sequence pi is pi if I is at most k and 0 otherwise. That is, now we are consider some percolation model truncated in the range k. That is, we erase all bonds with length at least k. And I will also denote by capital P k the probability measure on this model. And the truncation question is the following. Suppose that we have percolation in the original model with positive probability, and is it possible to find some large enough k such that the model still percolates if I truncate it with parameter k? Or in other words, the infiniteness of the range is indeed crucial for the occurrence of percolation? Is it clear for everybody what's the truncation question? Silence, I suppose that, okay, it's clear. Then, if I consider this model in one dimension, the answer for the truncation question is every negative, unless if trivial cases where one of the parameters pi is equal to 1. Suppose that all terms of the sequence is strictly less than 1. Then fix some k, some integer k, and divide the line in blocks with length 3k, for example. This distance is k. Then I define this block as bad if and only if all bonds starting from the middle third are closed. Then, if this is less than 1 for all possible lengths, then with some strictly positive probability, each block is bad. Then, by Borel-Cantelli's lemma, we have infinitely many bad blocks with probability 1, and infinitely many bad blocks avoid percolation with truncated parameter k. Then, for any k, it's impossible to see percolation with probability, with positive probability. And then this question makes sense only for d at least 2. For d equals to 1, indeed, the main question is not the truncated question, is to describe how the sequence Pn must decay for the occurrence of percolation. And in this direction, the main result is this classical paper of Newman and Schumann. In this paper, they prove that here, essentially, we are telling that Pn is something like some constant over n to the power s. If s is between 1 and 2, then we have a phase transition on this model, and we have percolation if the parameter P1 that controls the nearest neighbor intensity is large enough. It's not difficult to think that if S is strictly less than 1, the system percolates using Borel-Cantelli, for example, and if S is strictly bigger than 2, there is no percolation. But the case S equals to 2, there is still a phase transition on this model, but here the phase transition, again, we need this P1 large enough, but we need also this constant beta is strictly bigger than 1. This paper of Newman and Schulman is essentially the percolation version of 2 seminal papers in mathematical physics about the Ising model, long-range Ising model. Essentially, this first result is the analogous of the Dyson result for the long-range Ising model, and the second one is the analogous of the Frolic-Spencer, result. Both results proved in the beginning, the early 80s. I'd like to emphasize that in this paper of Newman and Schulman was conjectured that the same behavior occurs for oriented percolation. Indeed, the first part, they proved that this is true for oriented percolation, but the second part was not clear if it's true or not for oriented percolation in that time, and this was solved almost 20 years later by Domingos Marchetti, Vladas Sidoravicius, and Maria Eulalia Vares, when they gave an affirmative answer for this conjecture. That is, if S is equal to 2, then we have also oriented percolation on this one-dimensional model. And returning to the case with dimension at least at least 2, I'd like to mention some previous results in chronological order. Perhaps the first result in this direction was this paper by Ronald Mester and Jeff Stife. Here, they consider some long-range bond percolation model when the sequence Pn decays exponentially, and there's percolation with positive probability, because this hypothesis is not enough to prove percolation. Then there's this exponential decay plus percolation. Then in this case, is it possible to prove that they prove that the truncation question has an affirmative answer. The second result, not this second result, but probably all of these results from this, we can consider some stronger version of the truncation question is the following. Now we have some, it's given some epsilon positive and the sequence Pn. And here we have a kind of anisotropic long-range percolation. In one direction, we have long-range bonds, where each bond is open with probability given by the sequence. But in the other directions, we have only nearest neighbor open with probability epsilon. Then one more stronger version of the truncation question is the following. Given any epsilon positive and the sequence Pn such that there is percolation, is it possible to find some large case, blah, 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 blah. And in this contest, Donata Surgailis, Vladas, and Eulalia gave an affirmative answer for d equals to 2 if the sequence Pn decays like 1 over n log n. Later, this result was generalized by Menchikov, Vladas, and Marina Vashkovskaya. Essentially, it's the same statement of the result of Donatas, Eulalia, and Vladas, but now the hypothesis about the sequence Pn is a little bit weaker. For example, Pn could be 1 over n log, 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 how many logs you want. Another result about the truncation question is a result of Neuenberger in 2002. Essentially, this result is part of his PhD thesis. They prove that if the sequence Pn decays at least like 1 over n to the power alpha, if alpha is between d and 2d, then we can truncate it. And following the chronological order, in 2004, with Sasha Friedli and Vladas, we prove essentially the same result, the same conclusion, but now our hypothesis is lim sub positive. Okay, lim sub positive. This, of course, does not imply that the sequence Pn goes to 0. We can have some very heavy tails, but something new on this paper is that this was the first result where some very lacunary sequence is allowed. For example, in all of these previous results, we need something like this. When I say, for example, Pn decays exponentially, I'm telling that there exists some n0 such that for all n bigger than n0, Pn is like this. In this case, we can, it's allowed to consider sequence Pn such that we have infinitely many ranges where Pn is 0. But of course, it's weaker than Pn, the sum of Pn diverse.
Bernard, just
yes?
to be sure, the statements of the two first papers, I mean, so the assumptions are on the Pn, but the difference with the force, which is of Berger, I don't understand really. So Berger, it's saying that for any Pn larger, the difference with the three first result is that, for instance, and Menshikov, Sidorabisius, and Valshovskaya, it could not be 1 over n squared, for instance. It has to be 1 over n. It cannot be 1 over n. It has to be 1 over n log of this. When you say these two of the order, what do you mean?
Repeat only your last sentence, please.
Okay, so my question, I guess, is what do you mean by of the order? Where you use your two small waves. What does it mean formally? You see the small...
Are you telling about the Berger result?
Yeah. So the first three results, they have assumption on Pn, how do you say this assumption? It's of the order 1 over n log n. That's it.
Yeah.
What do you mean of the order? You mean that the ratio goes to 1? Because
yes.
Intuitively, what I was expecting is that the slower it goes to 0, the better. So in somehow, Berger, it's natural for me, because Berger is saying that, okay, if you take 1 over n, it's covered in his result.
Probably you are right. Here, probably this is not a bigger. This is something like there exists some constant, let's say C and capital C, such that Pn is between C1 over n to the power alpha and this. Yes, I'm sorry.
Okay. I don't understand how these results are in order of generality, because So there are just different assumptions, really. We cannot compare, or we can compare these assumptions.
No.
Okay.
Can I add something? It's just that, for instance, I don't remember exactly the statement of the Menshikov-Sidorov-Vertikovskaya, but if I'm not mistaken, they ask that the probability is decreasing, Pn is decreasing, and this is an extra assumption that's not written there, but
Yeah.
it's not a hypothesis.
Okay.
Okay, sorry.
Okay. And some years later, again with Sasha, we proved that without any extra hypothesis, only the divergence of the sequence Pn, then we can truncate it. But we can prove this statement only for dimension at least 3. The case d equals to 2 is still an open question until today. And I also would like to mention that none of these results work for oriented percolation. And another work related to the truncated question, but not only about this, is this very interesting example. I would like to thank Arnold van Enter for pointed out me this paper. In this paper of Biscup, Lincoln Chase, and Crawford, they study a three-state spots model, and we have exponential decay and percolation and phase transition, but the truncation question has a negative answer. Then it's an example where we cannot have an affirmative answer except the case one dimension. And okay, now I will treat about the oriented model, and from now on I will consider this graph. The set of vertices is ZD times Z plus, and the set of bonds is the following. From some vertex, let's say Xn, where X is in ZD and N in Z plus, we have bonds, oriented bonds, pointed for some vertex X plus I times some coordinate vector, and the last coordinate is n plus 1. That is, all bonds are oriented in the last coordinate. And again, we can define a long-range model on this graph. Is given the same sequence pi, and each bond will open with probability pi, where I is the length of the bonds. All bonds are open independently of each other. And like in the non-oriented case, if the sequence Pn diverges by Borel-Cantelli's lemma, it's trivial to see that we have percolation with probability 1 in the non-truncated model. Then, given some sequence such that sum of Pn is infinite, we can ask about if the truncation question can be, we can give some positive answer for it. And indeed, we can ask something a little bit stronger, is that suppose that we have percolation, And the truncation question is about there exists some k large enough such that the probability of percolation is still positive in the truncated model, but indeed we can ask a little bit more. That is it possible to show that the probability of percolation goes to 1 when the truncation parameter goes to infinite? Then, about this question, we have two partial results. Sorry. The first result is a joint work with Van Enter and Daniel Valesin. We prove that only with the divergence hypothesis, we prove that, okay, we know that we can prove that this limit is 1. But observe that this is true only if D is at least 2. Observe that in the oriented case, D equals to 2 essentially is a 3-dimensional graph. Our graph is dimension D plus 1. And the other result is a joint work with Caio Alves, Marcelo Hilário, and Daniel Valesin. We prove that in the dimension D equals to 1, if lim sup is positive, then we can give an affirmative answer for the truncation question on these oriented graphs. Essentially, these results when extend the previous results with Sasha and Vlada's proof in the 2004 and 2006. Okay, then the situation when D equals to 1, and sum of pi m diverge is still an open question. Then our main result is the following partial result. This is a joint work with Alberto Campos. Alberto was my master's student. Now he's a PhD student in Lima under the guidance of Augusto Teixeira. And our main result is the following. Consider this oriented graph for D equals to 1. If sum of P n square diverge, then we can give an affirmative answer for the truncation question. More than this, the probability of percolation goes to 1 on the truncated model when the truncated parameter goes to infinite. Now I would like to give some ideas of the proof of this result. Then, given the sequence Pn, let's fix some integer k. For example, the first range where Pn is strictly positive, and fixed some vertex xm, we will define these families of events. The event L is essentially, it's easy. The event L is, we have here the vertex x, m. Then this vertex, this bond is open, x plus k, m plus 1, and this is open, x plus 2k, and here m plus 2. Essentially, is two consecutive bonds open, where this k is this special k that I fixed. And I define also the event Ri. The event Ri is essentially only this. Here is the vertex x, m. Then this bond is open. Here is x I m plus 1, and this is open. Well, here is x m plus 2. And this is the event R max. The event R minus essentially is the same, but here this zigzag is point to the left side. Okay? And I define also this event S plus, and the key event is this event T, but it's better to explain these events X and T with this picture. Our main event is this, the event T. And the event 3 is the intersection of 3 events. The first event is a chain of several events like S. This event in red is this zigzag. Here is the vertex xm. Then, starting from this vertex, we have this zigzag. Okay? And the second event is essentially the same, but here I'm starting from the vertex x plus 2k m. And the third event is telling that from some vertex in the red zigzag, I have start the event L. That is, we have this line connecting the blue zigzag to the red zigzag. And essentially, this is the event T plus. Is plus. The event 2 minus is essentially the same, but now the zigzag both zigzags are pointing to the left side. Okay? This is our key events. Now, it's easy to see that the probability of the event L is pk squared. Then, given any epsilon positive, I will fix large integers m and k, satisfying these two equations. The first is trivial. It's only to find some large m such that this is less than epsilon over 3. And the second, is it possible to find this large k? Because this is due to the hypothesis that the sum of pi squared diverges. It's very important for us that all these events are independent, because we use disjoint bonds. And the probability of the event S, this is a simple computation. We have this lower bound for its probability. Then, if I consider this event T, by definition of the event T, we can see that these 3 events, the blue zigzag, the red zigzag, and the purple straight line, I'm using different bonds. Then all of these 3 bonds are independent. Then we can compute the probability of the event T, and event T occurs with probability at least 1 minus epsilon. That is, we have some control for this probability. The event T occurs with probability close to 1, as I wish. And another very important feature of this event is that here the maximum bond, all of the bonds that are used in the definition of this event has length at most n. Then essentially, if I consider the truncated, if I consider the truncated version, I can. Is it possible to find some large truncated constant such that the probability of this event t is again at least 1 minus epsilon, even for the truncated measure. Now I will make a renormalization. I will define some oriented renormalized graph. My oriented renormalized graph essentially is one octant of C2. This is this graph. Essentially, this is this graph. And we can observe by construction that if the origin, in the original lattice, if the origin, suppose that here is the origin, is connected to the vertex xm, and starting from this vertex occurs that magic event t, both zigzags and that straight line connect them, then the origin is connected to two special vertices here. More precisely, these two vertices. That is, suppose that the origin is connected to xm, then if the event t occurs, then the origin is connected to these two special points. Okay? And given some subset of vertices of the renormalized lattice, I define the exterior boundary of the set A as the bonds. Suppose that here is the set A, for example. Then the exterior boundary is the vertices out of the set A, is strictly above other vertices. Oops, sorry. For example, here and here. Okay. And now I will define some exploration process on this renormalized graph, and this exploration process has two important properties for me. The first property is that if occurs percolation on the renormalized lattice, then this will imply in percolation on the original lattice. And the second property is that if some vertex on the renormalized lattice is connected to the origin, then this vertex, then this will imply in important crossing in the original lattice. More precisely, I do this. This is the construction. We will define inductively a pair a pair of subsets of the set of vertices in the normalized lattice. In the beginning, we set both sets equals to the empty set, and I will define the vertex T0, U0 as the origin. Then, given the pair AN, BN, are you looking for if there exists at least one vertex on the exterior frontier of the set AN, but outside of the set BN? That is, in some sense, AN and BN are the set of explorated vertices. AN is the set of good vertices, and BN is the set of bad vertices. Then, in each step, I'm looking for some non-explorated vertices, and if this vertex does not exist, then I stop this exploration process and I tell that there's no percolation on the normalized graph. But if there is at least one vertex on this graph, then I fix it on some vertex, let's say Vn, Un, and I will define the next pair of sequence, An plus 1 and Bn plus 1, as follows. Starting from some special vertex, for a while, does not matter who is this special vertex. Are you looking for if this event An occurs? Essentially, this event An, this event E, is the event T plus or T minus, depending of this coordinate, if this coordinate is even or odd. And if this event E occurs, then I declare the vertex Vn, Un good, and I put this in the set An plus 1. Otherwise, I define this vertex Vn, Un as bad, and I put it in the set Bn, the set of bad vertices. That is, this is the renormalized process. On the right, we have the renormalized graph. On the left, we have the original graph. Then, in the first step, I try if occurs the event T plus starting from the origin. If this event occurs, okay, the origin is good. Then the origin is red. Red is good for me. Now, the next vertex is this. Now I will try to see if this vertex is good or not. Then I will looking for if from in the original lattice is from this this pink point starts the special event T. Suppose that no, there is no some event T is starting from this point. Then I declare this vertex on the renormalized lattice as bad. Now I will try this vertex. For this vertex, I will looking for if I start the event T from here. Okay, we have some event T here. Then I declare this vertex as good, and so on. Then, for example, the next this vertex is good because you start some event t starting from here. As well, this is good because starting from event t starting from here. In the next step, for example, are you looking for if this is good or not? If this is good or not, are you look for some event t starting from here? Okay? Is it clear, this exploration process? And now I define A infinite as the union of this set of red or good vertices, the set AN, and the following lemma. Essentially, this lemma is part of some extensive lemmata in this Grimmett and Mastron paper about percolation of slabs. This is exactly the first of these lemmas. Essentially, this lemma is telling the following. If in each step, the probability of the set Bn is equal, Bn plus 1 is the same of Bn, that is, the vertex with index n plus 1 is good. If this occurs with probability at least some gamma, where gamma is strictly bigger than the percolation threshold for the oriented percolation, ordinary oriented percolation, then the probability of percolation on the normalized graph is bigger than some positive constant, and this constant goes to 1 when this gamma goes to 1. Indeed, in the Grimmett and Mastron paper, they proved this lemma for the non-oriented case, but the proof is exactly the same for the oriented case, that there is nothing special on this proof for the non-oriented case. Then, using this Grimmett and Mastron lemma, essentially observe that by construction, the probability of each vertex is good is essentially the probability of the specific event t plus or t minus occurs, and by that appropriate choice of constants, this probability is at least 1 minus epsilon, and this epsilon, we have freedom to choose this epsilon. Then, using this Grimmett and Mastron lemma, we can conclude that there's percolation on the normalized graph, and this implies percolation on the original lattice. And again, I emphasize that in this construction, in the definition of the event 2 plus and 2 minus, I use only bonds with some bounded length. And perhaps I forget to mention this question of 2 plus and 2 minus is to guarantee independence of these events. That is, in each layer, for example, here in the first layer, I use only events of type 2 plus. Here, only 2 minus, and so on. This is important for us to to ensure independence among these events. Okay, here I finished the sketch of this proof, and I would like to mention in some senses, a trivial corollary. The corollary tells the following. If the sequence Pn satisfies at least one of these two hypotheses, then we can truncate it. The proof is very simple. Essentially, both these hypotheses implies that the sum of Pn squared diverges. Then it's a trivial application. But I'd like to mention this corollary for the following reason. Now, I will modify my graph. I will consider some anisotropic version of long-range percolation on C2. Essentially, I will consider the same graph considered in the paper of Hilário, Donata, Surgailis, and Vladas Dravicius, or Menshkov, Vladas, and Marina. We have long-range bonds on the horizontal direction. In the vertical direction, we have only nearest neighbor. And that is, the set of bonds is the vertical bonds, nearest neighbor bonds, and we have long-range bonds on the horizontal directions. And we have as parameters the sequence Pn. Each horizontal bond is open with probability Pn, where n is the length of the bond, and each vertical bond is open with probability delta. Okay? And now I will consider a percolation model on this graph, where, of course, all bonds are open independently of each other. Then we can prove the following result. Given any positive delta, if the sequence Pn satisfies at least one of these hypotheses, A and B, then we can prove the truncation question. That is, the probability of percolation on the truncated model goes to 1 when the truncated parameter goes to infinite. Observe that these hypotheses N, A, B are the same hypothesis of the corollary. But I would like to mention this because for this graph, we can prove truncation question with hypothesis A or hypothesis B, but at least Alberto and me, we don't know how to prove this if I consider only this hypothesis. Okay? And Aline, how much time I have?
5 minutes at most.
5 minutes.
Yes.
Okay. In these 5 minutes, let me give a very, very brief sketch of the proof of this, at least of the part B. Part B, in my opinion, is more interesting than part A. For part B, the key result is to use this lemma to Kalikov and Weiss. Essentially, this lemma is the following. Consider some independent long-range bond percolation on the one-dimensional graph, and suppose that the sequence Pn diverges, and the greatest common divisor is 1. Under this hypothesis, given any segment with length L, suppose that here's the origin, this is L, we can find some large capital L, such that all vertices on this on this small segment are connected using only bonds in the larger box. That is, all of these bonds, all of these vertices here are totally connected inside the segment 0 to this capital L. And essentially, with some appropriate choice of the parameters and use this Kalikov-Weiss lemma, I can define some set of events, but my time I not defined properly. But the key event is the following. I will call it again T, the event T. Então, suppose that here is the vertex X. In this example, X is the origin. The event T is the intersection of 3 events. The first event is a pink event. Essentially, the event AX is the following. It's like the event given the Kalikov-Weiss lemma. All vertices in this pink segment are connected using only bonds inside this segment from the origin until this capital L0. Okay? And the second event is a red event, essentially is the following. We have one vertical bond, one nearest neighbor vertical bond open, then I go to the left, return, I go to the right, I return to the left, and again, I go up another vertical bond with length 1. And the blue event essentially is almost the same. There are only 2 differences. The first difference is that the red event starts in the first half of this pedestal, and the blue event starts on the second part of this pedestal. And the second difference is that in the blue event, I go first, like in the red event, I go first to the right, but I go the short jump to the right and the long jump to the left. In the red event, I make these jumps in the opposite order. Then again, I define some renormalized lattice, and I can prove that by the appropriate choice of parameters, this event T occurs with probability as close to 1 as I want. That is, given some epsilon, I can find appropriate constants such that the probability of this event T is at least 1 minus epsilon, and I use, for the construction of this event T, bonds with at most some capital K, with length at most some capital K. That is, even for the truncated model, the probability pk of this event Tx is at least 1 minus epsilon. Again, using this appropriate choice of R minus and R plus, all of these events are independent, and here is the situation in the renormalized lattice. Here, the renormalized lattice is 1/4 of Z2. Then, for example, the origin is good if, starting from the origin, we have the event T. That is, that pedestal. Now I'm doing some abuse of my drawings. This red straight line is not indeed a straight line. These are these four bonds defining the red event. That is the event in this picture. The event T is the pink pedestal plus, starting from the left side, something going to appropriate place here, and something starting from the blue part in some appropriate place here. Here. This is the event T. And observe that if I start from here to look if occurs another event T, does not matter where this where I arrive, does not matter, because this this pink pedestal is totally connected. Then, if occurs the event T is starting from here, does not matter when the previous event arrives, we have this connection. Then, if we have a percolation of this event T on the renormalized lattice, this will imply percolation on the original lattice. And essentially, this finished this very, very brief sketch of the proof. And this hypothesis of the greatest common divisor is 1 is not very important, because if this divisor is not 1, is strictly bigger than 1, for example, D, we have the same construction, but considering not Z plus D, but consider now dz times Z. Okay, I think that I finish here, and thank you very much for your attention.
Thank you, Bernardo. Do we have questions or comments? I think Alberto want to say something. I think it's Alberto. No?
It's time for questions.
Yeah. Do we have questions or comments?
Okay. Maria raised her hands, which is the right way.
Go you first, Sandro. I can do it. No, I wanted. So first of all, thank you very much, Bernardo. I wanted to make a question and have a small comment. The comment has to do. I didn't want to bother you at that moment when Sandro asked about this old paper. But our condition, at least, is that for large I, pi is bigger or equal than 1 over I log of I. And I believe the one of Menshikov and co-authors is exactly the same, replacing I log I by I log I. So these are this is just a comment. In the case of the other direction was nearest neighbor, but I don't see, so of course, these two are comparable, of course, the extent. But I think I don't see comparison with, because Neuenberger's result is in all directions, is not nearest neighbor, no? You have PN, so I don't see how to compare.
Yes, exactly. In the Berger paper, it's important that we have long-range bonds in all directions.
Yeah, yeah. So now, Bernardo, something that puzzled me a lot, maybe you could show it again, was the result you mentioned very briefly. I don't remember now if with Daniel Valesin, something on the one-dimensional case. So one-dimensional, I got a little bit lost. If you could show it again, because I got really puzzled. What was because truncation in one-dimensional to me looks always complicated.
No, it's D equals to 1, but D equals to 1, it's a two-dimensional graph.
But what was your, because your graph was
yes,
ZD times Z. What was your graph there? Maybe I got lost at that moment, that's why.
Here.
Okay. That's okay.
The time
so,
is D times Z plus. Essentially, one is a two-dimensional graph.
Yeah, okay. Now it's like oriented in the time direction. Yeah, okay.
Yes, essentially this result of with Van Enter and Valesin is the analogous of this result of Sasha.
Yeah, now I understood. It was my stupidity. Sorry, I got lost. Okay.
Because in this result of Sasha, our proof is it's necessary the non-oriented case.
I see. Now everything sort of got.
And essentially, the second result with Caio, Daniel Valesin, and Marcelo Hilário, it's the analogous of this result for the oriented case. Yeah, these results.
So thank you.
Do we have more questions or comments?
Yes, I have a very simple question, I guess, because actually I was also asking myself about the graph. So the graph, you may have connections between a guy with a guy which is above it at any place on the left, on the right, if D is equal to 1. This is it?
Could you repeat, Sandra, please?
No. So a guy at take when I see the definition of your graph, I get lost. So the picture in my mind is that a guy can connect to a bunch of people which are above him. This is it?
Yes. Essentially, we have the two results that I presented are concerning two different graphs. In the first graph, for example, the main result, the graph is this graph that you mentioned. From this vertex, consider here one line. I have bonds from here, only to the next level, but for all ranges. Okay.
This was about this model. So my question was just a simple question. If you just allow to connect on the right, that is completely oriented, not only that you go above, but you go only on the right. So in this case, it's a tree. What will be the condition on the P, just to know?
Good question. Indeed, we need the non-oriented. We cannot orient it all directions.
Well,
I
but
can orient only the last coordinate.
But so in one dimension, you meant that you can only orient it going above. You cannot also say that you go only on the right. That's it?
Yes.
Yeah.
But if you go only on the right, the problem is much more easier because you cannot. So it will be, you construct like, you are constructing a Galton-Watson tree, no? And then the condition should be very easy to get. Well, my question would be, how stronger has to be the condition on the, if you only go to the right in relation to your condition? But perhaps you don't know what is the condition if we go only on the right.
Well,
perhaps I'm saying a completely stupid fact, things, because I was expecting that it would be much more easier to go only on the right and that we could have a very easier condition in this setting.
no, for example, if in this case, if I can go only to the right, I don't know how to prove this here.
No, you're right. It's not a tree. No, okay, it's not a tree as well. It's not easier. Okay,
Yes.
Sorry.
But, for example, the previous result, this result with
No, you're correct. Sorry.
this result
sorry,
with Caio Alves, Marcelo Hilário, and Daniel Valesin. In this case, indeed, we can prove this condition for the truly oriented graph. Is oriented in all directions. But in this case of with PM square, I can orient it only in one direction.
Okay, thank you. Sorry, my question was stupid. I get lost. Okay, thank you, Bernard.
I think Luis wants to say something.
Can I ask a question if there's no one else? Can you hear me?
Yes.
Okay. So yeah, it's not directly about this truncation problem, but I mean, it's. I even apologize if this I had if I have asked this question before but well, I mean, what I wanted to ask is that. As far as I remember, this truncation problem came from Henrique and Henrique Angel and this was problem number 2 that he posed, and there was problem number 1, which was, I believe, stronger. I don't know if you know about this, Bernardo, but I was going to ask about problem number 1, which I'm not sure even if I can remember the correct formulation, but I could try. But in any case, it's mainly for the. I mean, the question is mainly for the case you know about this and remember. I mean, if there's anything that you know about the stronger version or the I don't know the other problem that Henrique posed at the same, more or less at the same time.
No.
Yeah, I mean, it had to do with.
If I understand correctly, the question proposed by Henrique is exactly the same context of the second result. Huh? We have only oriented bonds. We can think about a 2-dimensional case, 1 + 1 dimension.
Right.
We have horizontal long-range bonds and only nearest neighbor vertical bonds.
Okay.
Vertical bonds are open with probability epsilon. And suppose that the sequence Pn diverges. Then is it possible to truncate it? As I understand, this is the Henrique question.
Right. Yeah. This is what I was calling problem number 2. There was a problem number 1, but it's okay. Perhaps you don't know about this, and so it's okay. I mean, it's just I was just curious whether what would be the status of this other problem.
Okay.
I'm not sure whether where
what
this.
are you calling
it's-
problem number one is it's only the truncated.
It's something without
without
truncation. Yeah, it's something without truncation. It's but it's finite range. But it's sort of arbitrary finite range model. It's another question. But if I remember well, and I even asked Henrique about this recently, and he more or less confirmed, but I'm not sure. But it's okay. I mean, never mind.
Okay, if you allow me some comment, indeed there is some stronger version of this question. This stronger version, in some sense, Vladas and me, we tried to think that a long time ago. I was a PhD student at that time. Essentially, is the following. Given the sequence Pn, there exists some large K, such that if sum of Pn is bigger than K, then there is percolation. Essentially, this K depends only the dimension. This implies in truncated question.
If I remember well, this is close to what was called problem 1, but maybe I messed up.
Yes. Indeed, in that time, we wrote some drafts, but it's not a very important result. Indeed, this is true on trees. This stronger version of the truncated question. And probably it's also true for high dimension. And the argument for high dimension is not this sophisticated tools like lace expansion. It's a trivial argument.
Depending on, I mean, only now anyway. I don't.
Can I consider as answer to your question, please, Renata?
Yes, thank you. I mean, my question is not a question. Yes. But thank you, Bernardo. That was a very nice talk. And I mean, I just would like to comment that in the beginning you said that you were losing your time with this, and I would. I was going to say that it is not losing time. I mean, perhaps you meant spending time, but in any case, it's time well spent. Thank you.
And as Sandro wrote in the chat,
Yeah.
As a result, you have very nice modern art in your proofs, Bernardo. So,
what is the synonyms of ugly pictures?
Not at all, Bernardo, not at all.
Yeah. I think we just run out of time, so let's thank Bernardo again. It was a really nice talk, Bernardo.